Hello, everyone. How are you doing? Did you grab your lunch already? Yeah? Perfect. It's important to not stay in the way of the lunch. That's very important. So I'm Maxim Lukianov, Program Manager on Azure HDInsight team. That's a big data service on Azure that offers Hadoop and Spark open source technologies in a managed form factor. I work primarily on Spark technology, and today we'll talk about building modern data pipelines with Spark on Azure HDInsight. Okay, let me switch. So in this talk, we wanted to basically cover a very important, switching my machines. Cover a very important topic of building big data pipelines or patterns of how we can approach that. And this topic is actually very broad in scope. Like there are multiple technologies on the open source side, on the Azure side that you can use to do that. So in this talk, we scoped the question with one kind of insight that we gained from our customers. Like more and more times we see customers coming to us and saying, hey, one simple choice that I have already made is I decided to go with Spark. But so now that this decision is made, how do I build the end-to-end pipeline around it? So what other technology choices I can make? So to help with this kind of line of thinking, we decided to give kind of an end-to-end coverage of that problem and discuss what are these kind of key deciding factors that arise in the customer discussions that lead to one choice versus another. So in this talk, we'll talk a little bit about Spark and then focus on two types of the pipelines, batch pipelines and real-time pipelines. A great example of a type of the artifact that we'll be discussing is these architecture diagrams. They're awesome. They help us understand in a very simple kind of picture of how components are connected and how data flows through the system. This is an example of one of the architectures from one of our customers, Pros, the large ISV company that builds applications for various industries. And this architecture represents one of their applications, which is an airline ticket price recommendation application that serves thousands of sales representatives around the world, actually millions of sales representatives around the world. And it tackles fairly challenging problem. It says, hey, can we capture all of the real-time factors that affect this price recommendation? Then run some machine learning model that provides this recommendation, and in real time recommend to all of these millions of sales representatives correct prices, personalized recommendations. And that kind of represented here in these two factors. There is an interesting presence of both batch jobs and real-time jobs. But overall, aside from that complexity, this is fairly simple architecture. You can see there is even Azure SQL is used. And you would say, hey, if you're talking about processing big data, isn't it kind of a common sense to not use SQL? Well, it is actually possible to use SQL in an appropriate place or in an appropriate point. So in this talk, we'll go through these decision points and how we can build this kind of a simple yet powerful architectures, and discuss even how we can build in more complex architectures and when it's appropriate to do so. So there are three types of data pipelines. The batch pipelines, which process data on a periodic basis, fairly simple concept. A real-time pipelines where you process a stream of events in real time. And machine learning pipelines that deserve their own attention. But in this talk, we'll talk about the machine learning pipelines in the context of the batch pipelines or real-time pipelines. It is frequently the case that whenever you do machine learning, you either do this on a large volume of data and run your machine learning training process as a batch pipeline or as part of the batch pipeline, or you do the second part of the machine learning process where you score your models or produce the predictions at real time. And then you can run it as a part of the real-time pipeline. Later in this talk, at the end of the talk, I have a set of references to other talks available for you at Ignite, where these machine learning pipelines are covered in more detail. Okay, so first topic, let's talk about why Apache Spark, why we see this kind of decisions being made to standardize on Spark. And throughout the talk, feel free to ask questions. We do have a set of kind of tables that compare technologies, and they're kind of rich in information. So I'm going to highlight some of the key points about these tables, but if something is interesting to you or you'd like to clarify something, feel free to ask, and then we'll be able to kind of dive in the areas that is relevant to you. So if you're, by the way, how many of you are familiar with Spark or big data in general? Raise your hand. About half, 40%. Thank you. That helps us kind of establish the bar of at which we should talk about it. So if you're new to big data world, you're coming at a kind of a good time. In the past, in the world of Hadoop technologies, the world was very kind of fragmented. There were multiple technologies that allowed you to do many things, but they were all very different. If you wanted to do machine learning, you would use something like Mahout, but Mahout was like a command line utility with its intricate kind of command line syntax, and you would need to learn that. If you wanted to do some SQL analytics at scale, you would use Hive. And that's just a dialect of SQL, but it has nothing to do with Mahout. And the same applies to all of the other technologies that existed in Hadoop. They were kind of very separate from each other. And this is when Spark came in and kind of unified the world. The idea behind Spark is that it provides this unifying compute engine that provides very nice APIs in a multiple of languages. It supports Python, R, Scala, Java, and SQL, of course, if you like SQL. And on top of that set of kind of unified APIs, it provides libraries that are specific to a particular use case. You can do streaming with Spark, you can do machine learning with Spark. And the good thing about this kind of layering of abstractions, as we kind of all know, is that once you learn it, once you learn this kind of a common ground, then it's very easy to learn a specific implementation that applies to machine learning or on some other domain. So that's one of the driving factors that kind of resulted in more and more customers adopting Spark. And now it's easy to say that the set of Hadoop technologies of big data is kind of throughout the industry is converging on Spark as a common computation engine. So far, Spark growth isn't slowing down. It's already kind of the top project in terms of number of contributors in open source world. And as you can see, in the last year, the number of contributors have only grown. There is, of course, some challengers to Spark, like alternative technologies. One of the recent ones is a technology called Flink. So a couple of years ago, it was introduced, and it provided better kind of support for streaming. And it generated a lot of interest and attention. And people were saying, hey, is Flink going to replace Spark? Well, as it turns out, Spark didn't kind of stay on its place and actually moved forward and fulfilled all of the gaps that this Flink as a challenger was providing it in a streaming space. And in the past couple of years, we see that interest in Flink kind of didn't grow, but instead the interest in Spark continues to grow. So one of the important kind of this innovative pieces in Spark that reinforce the interest from community in it is a couple of things. The first is a project Tungsten. That's a project that spanned a couple of years and resulted in the invention of Spark 2.0. This is basically an end-to-end approach of improving performance of Spark and resolving some of the performance challenges that Flink originally addressed and that were actually common to any big data processing technology based on Java virtual machine, which is Spark. So this project Tungsten, Spark now provides provides you with a new compute engine that bypasses Java virtual machine. It uses some low-level bytecode generation, and basically provides improvement in speed in the order of 3 to x compared to the previous kind of results from Spark. And at this point is a leading in terms of performance across all of the big data processing engines in open source space. And recently, so Spark 2.0 was introduced a year ago, and about a few months ago, Spark 2.2 was released, and that version addressed the set of challenges of weaknesses in the streaming space, and provided a kind of a new structured streaming support that addresses some of the limitations in terms of windowing functions in Spark. And one important feature that is now available in Spark is a new continuous mode of processing of real-time events, and that allows it to achieve kind of very low latency of real-time event processing, something that was a challenge from competing projects such as Splink. So as a result, the set of kind of areas of growth for Spark includes streaming and the new APIs, data frame APIs that are based on the project Tungsten. So the growth of Spark continues. Any questions so far? Any particular aspect of Spark that you wanted to learn about? Okay, so let's dive into the batch pipelines. So there are multiple patterns in terms of how people approach batch pipelines, and the most common one, the most straightforward one, is a periodic ETL or machine learning. ETL stands for extract, transform, load. So in this scenario, we are basically talking about a very basic kind of idea around processing big data. I have my data set. It probably updates every day or more frequently. And once it's been updated, I want to run my batch process and clean this data, join it maybe with some reference data, run my machine learning models to produce some insights, and output the result in some storage. And in the context of Spark on Azure, we are talking about variety of technologies. So Spark cluster itself is provided by HDInsight, and as an input and the output, Spark can actually consume data in multiple formats and storages. So in terms of storage technologies, Azure Blob Storage or Data Lake Store can be used. But Spark can also directly connect to external data sources. There is a website, sparkpackages.org, that provides you with the documentation of all of the packages available in the open source ecosystem for Spark. And it has more than 50 packages connecting to Cassandra in a variety of data sources, including SQL databases, SQL Data Warehouse, and new popular option, Cosmos DB. One of the requirements that span from this kind of pattern for the engine that organizes your data pipeline is that not only you want to run like a single job that does this processing of the data, you probably want to run multiple of them. And these jobs form of a graph. Like if original job that parses the data didn't succeed, you probably don't want to run the job that produces analytics based on the result of the first job. So that requirement of the data pipelining engine to understand dependencies between jobs is something that we'll see is a driving factor in the choices that you make about the data processing engine. So, what kind of choices in terms of ETL language or how you do the ETL processing in big data space today? Well, as I said, back in the days, the choice was fairly complex. There were multiple languages like Pig and Hive and Spark and Flink, all of these kind of new entrants. But today, as you can see from this table, if you compare green to red, the choice becomes kind of fairly simple. And that's a good thing because now we don't need to think that much about this all of these choices. There are many other choices that we need to care about. So just to highlight a couple of things here. So Hive as a SQL dialect is a great SQL language. But when it comes to the ETLs and kind of sequential nature of the ETL process, where extract some data and use the results of this extract as an input for the next stage of your data processing, this kind of sequential set of iterations, doesn't lend itself very well for SQL. Like in SQL, you'd implement this either with some form of a very heavily hierarchical SQL query, where you would chain queries one after another. Or you would output the results of one query into a temporary table, and then use this temporary table as an input for the next SQL query. And that kind of temporary table creation is a performance hit. It slows down your jobs and makes your kind of scripts not work that well. So that challenge is addressed by both Spark and Pig, in Spark language, it's available. In Spark, it's also available in the language of your choice, such as Python or R. Another factor, and that brings us to another factor of languages. Across the spectrum of programming languages, Python in recent 4 to 5 years has grown tremendously amongst data scientists, but also amongst data engineers. So if you haven't looked at Python, maybe it's a good time to take a closer look. The next pattern that comes very frequently in our customer discussions is incremental data processing. When we are talking about big data, we are talking about terabytes or maybe petabytes of data, and processing the same set of original data of inordinate sizes every time is kind of inefficient. That's obvious. And in many cases, especially when it comes to a fact table, like think about transactions or some events, in many cases, the data naturally is additive or appendable. So on the new morning, the set of data that needs to be processed just nicely partitioned into some date range. And in principle, we just need to process that data and don't need to touch results of the previous days. So that drives this incremental data processing idea, where the set of files and folders in some storage is being populated with the new data. Or let's say we put it in a new folder. And then we just run our big data processing jobs against this increment, produce new increment of the output that can be used in our data warehouse or for analytics, and place it into our data warehouse. And this is where we introduce a notion of the partition, and we don't have time to kind of spend much on discussing Hive partitions here. But that's a kind of natural mechanism that is shared between Hadoop systems based on Hive and Spark based on Hive. And that is a mechanism to append data to your Hive tables in an incremental manner. In the end of the session, I have a reference where you can learn in more details about Hive partitions if you're not familiar with them. But for now, just think about it as a mechanism to append to your table. Again, once we process this data, we can output it either into kind of a file storage, where our Hive tables can read the data from, or into a structured store as well, such as SQL or Cosmos DB, or even back to HDInsight cluster, which can mount like these Hive tables on top of the blob storage or data lake storage accounts. So now that we kind of learned how to process our data incrementally, and we have also ability to process data in bulk using our ETL jobs, we are coming to a very central pattern in the cloud. This is actually the reason why big data projects in the cloud are so popular these days, is this ability of using compute resources on demand. That's a unique property of the cloud. And maybe you're very much familiar with that, and it's no news to you, but this is an important concept to emphasize because it takes additional kind of work to switch from kind of always running data pipelines to pipelines that run on demand. And that drives another set of requirements for your data pipelining engine. So in this scenario, in this architectural pattern, we are talking about basically reducing our cost by virtue of on-demand computing. Before we run an ETL job, we create this cluster that provides us with compute resources. Then ETL job processes the data that is stored in the storage system that resides outside of the cluster in Azure Blob Storage or in Azure Data Lake, and then writes the data back into this external storage system. And in the process of doing so, the cluster that actually performs the data processing remains stateless. So there is nothing in the cluster itself that we need to preserve in order to keep our jobs running. And that allows us, at the end of the process, just delete the cluster and stop paying for these compute resources. Another advantage of that approach is that we can actually shrink the time it takes us to process the data, because now we can afford to scale out to very large clusters to demand very large amount of compute resources to speed up our data processing. That's another advantage of this cloud on-demand compute pattern. And this is something that we see our customers that move towards production deployments consistently implement using various means. So that's certainly something like a milestone in your big data projects, achieving this on-demand compute. So now that we kind of went through the set of very core scenarios for batch processing of data in the cloud, we have a set of requirements in mind. So what data orchestration tool is available to us in the cloud? So this is a landscape of data pipelining tools, and it's not exhaustive. It doesn't include everything. If we would include everything, it would be like probably about 50 of the projects. But this is the projects that are most popular amongst our customers. So this is certainly the type of project that you want to take a first look at. So on the Azure side, we have this great service, Azure Data Factory, which exists specifically for this purpose of creating data pipelines in the cloud. But it has some limitations that we'll go through. So it doesn't work or applicable in all of the cases. On the open source side, there is a great variety of projects. Airflow and Uzi are the topmost frequently used ones. Uzi is kind of a very old project. It's based on XML definitions of the data pipelines. And while we're fully supporting Uzi in HDInsight service, its popularity is going down. The more kind of new project is Airflow, and that's where some of the kind of better design decisions been made, and that drives its popularity. And we'll take a closer look at Airflow in the moment. An important other kind of category, the whole category of tools, is offered by third-party independent software vendors. And in HDInsight, we have an integrated marketplace where it's very easy for you to go and install some of these third-party tools. It does imply that you need to have a license from the third-party providers. These are not free tools, so you need to purchase them separately. But they do offer very high-level kind of end-to-end experiences for the problems that they address. And we'll take a look at the stream sets as one of the kind of nicer ones in this category. So depending on the needs, depending on your needs, you would move from built-in provided by Azure to very customized tool provided by third party. Okay, let's take a look at some of those tools. So we'll start with Azure Data Factory. So till recently, Azure Data Factory had some limitations in terms of its UI capabilities and stuff. And the great news of today is that version 2 of the Azure Data Factory is released. And in today's demo, we'll actually take a look at some core capabilities of Azure Data Factory v2. So what we see on the screen is as a resource group, we have a couple of resources, and we'll use this resource group to provision our on-demand Spark cluster that will process some job. So in this group, you will see that I already have Data Factory version 2 provisioned, and I have just a storage account. So the experience around Azure Data Factory, or how you create and kind of manipulate it, is right now based on the PowerShell. And while the team is actually in version 2 is working on the UI, I'm not going to demo it because the Azure Data Factory team will actually demo it tomorrow. And I don't want to steal this thunder. So if you want to take a look at the UI way of creating data pipelines, you're welcome to attend their session. I have a reference in the end of the deck. So for now, let's take a look at a simple PowerShell. So the first thing that you create the Azure Data Factory pipeline, which is just a very simple operation, and I already done it. And second, you need to create a pipeline. And this is a multi-step process. The first step is to create what's called linked service. Basically, it's references to the resources that your data pipeline will use. The first one is just a reference to the Azure storage account that you have seen. And the second one is actually an interesting one. It's a reference to the definition of the on-demand Spark cluster. So let's take a look at that one. Azure Data Factory experience is based on JSON. So in this JSON definition document, I define an HDInsight on-demand cluster. I define its size, the cluster type, some parameters related to login information, the version of the cluster, and the reference to the storage account. So once this is defined, we can actually run this. And it will prompt me to override the already existing definitions. And now I basically created definitions for this reference resources. So let's go back here. Should make this big. So the second step is to actually create the pipeline itself. And it's based again on the JSON definition file. So if we look at this pipeline, now you can see that it's references to the linked resources that we have created here. And inside of its definition, it actually references a Python file that will be executed as a job. So Azure ADF, Azure Data Factory v2 supports Python and Java jars as a job definitions for your service. So here's a very simple Python script that uses Spark to compute a value of pi. That's a very simple example. You can see here that it is expected to be stored on the storage location. So we have this file located on the blob storage from which it will be read. It will be retrieved by the job. Okay, so now we can create the pipeline. So let's go back. Create the pipeline. Okay, and override. And now we have all of the artifacts created in Azure Data Factory service. So now we can just run it. And we can instruct Azure Data Factory to run it on schedule, or we can just issue a one-off run using direct PowerShell command. So this run command invokes kind of triggers the execution of our pipeline. So I'll copy paste this little while loop so we can see a little bit of status of how this pipeline is being executed. So now the run is triggered, so we can see it is in progress. And if you go back to our resource group, the first step of this pipeline is to go and create a cluster. So we have specified all of the parameters of the cluster. So the pipeline will first create the cluster, then execute job on this cluster, and then delete the cluster. So let's see if it's working. So it will take a few minutes to create it. Okay, while it's working, we'll take a look at this later, I guess. Yeah, let's give it some chance to proceed. So the next, so while it's processing the request, the next technology that I wanted to demonstrate that is kind of provides a different experience in terms of managing your pipelines is Airflow. So that's an open source project that you can install on Azure HDInsight cluster and use it to trigger your pipelines. So Airflow takes somewhat similar, but also a different approach to Azure Data Factory. So in Airflow, the idea is to treat pipeline not just some kind of a random artifact on the side, but as actually a source code. So it says, hey, your data pipeline is actually part of your program. So it allows you to create pipelines in the form of the Python script. So just to take a look at how one looks, we can take a look at the simpler one. So inside of Airflow, you can just click on code and take a look at the pipeline. So this is a definition of pipeline. That's just a Python script. So the first you create a graph called DAG, and then you create an operations. For example, if you want to trigger some command line execution, you would create a bash operator and connect it to your graph using this parameter. And then you can even use some dynamic graph. You can generate some dynamic graphs by generating a simple for each loop or for loop, and inside of it create a multiple of operators that depend on the previous one. So that pipeline actually then creates a graph of interdependent nodes. And Airflow has a support not only for understanding these job dependencies, but also for understanding kind of a notion of the data lineage, where it says that, hey, if one job dependent on another have processed some snippet of the data, then I can proceed and execute another operator that depends on the output of that job. So if you look at the tree view here, we can see how it looks like. So this is the runs that this pipeline have done. And you can see that the green ones are the successful executions, and the absence of the square means that, hey, this part of the pipeline wasn't executed, and as a result, the overall execution here has failed. On the next run, all of the dependent jobs have executed, and the overall job has succeeded as well. It has multiple other ways to represent this information, including Gantt chart, where you can see the dependencies of the jobs. And if you go back into the overall view, it also shows you kind of stats about how many succeeded and how many of the runs failed. So that allows you to have some visual insight into how your pipeline performs. One of the powerful features of the Airflow is extensibility. So the fact that you are defining your pipeline in Python allows you to use the Airflow APIs to create your own types of nodes and incorporate them in your pipeline. And we use here an example of Livid job server submission operator of how you can integrate Airflow with Azure HDInsight service. So if you look at this guy, you can see that, hey, it's successfully implemented, it successfully ran several times. And in the code, you can actually see that we use this Livid Spark operator to submit Spark job to a job submission service called Livy that we use on HDInsight as a REST APIs for job submission. So that's an example of how you can extend Airflow with your custom operators, and it will still kind of do all of the data dependencies and data lineage kind of tasks for you. So another aspect of the Airflow is its orientation towards kind of DevOps flow of the work, and that can be illustrated here in the command line tool. So this data pipeline definitions or Python scripts that Airflow uses, they're just actually files on a folder on your Airflow host. And the framework around using Airflow assumes that you're just using your some form of the repository to get the latest versions of your jobs, or maybe development versions of your jobs. You just check it out from your Git repo, and then you test them. And after your test succeeds, you can deploy them into production. So Airflow provides these command line utilities, so you can integrate them into continuous integration and continuous development environment to test your new versions of the data pipelines. So let's try it out on our Livy Spark job. So that will submit the job that we just looked at into a Spark cluster. And to see its effect, we'll switch to a Spark UI. So this is an HDInsight cluster kind of resource management UI, where you can see all of the jobs submitted to the cluster. So right now, there is nothing submitted. You see the jobs are empty. And now if I refresh, you can see that a new Livy session 35 was submitted to the cluster. That's exactly the job that was spawned by Airflow. Okay, let's go back to our. Oh, it has finished. Oh, there is an error. Okay. Okay, let's try it again. There is some reference to the container in the cluster that is being reused. So that failed our job submission from ADF. Okay, one more try. Okay, in progress. I will need to resolve that error. Okay, that's unfortunate. But Airflow worked. So at least part of the demo worked. So let's move forward. So that shows you kind of two approaches to. Sorry, the question. Yeah, so I'm just about to go into the comparison slide between them. So that showed you kind of two approaches to the data pipelining in Azure. The first one is built-in Azure service, and second one is open source technology that you can treat as more of a do-it-yourself toolkit. So Airflow is very extensible, but you still need to install it. You still need to kind of add your custom extensions. But as a baseline for your own custom data pipeline engine, it's a great tool. Other questions? Yeah. Sorry, say it again. What are the connectors available for ingesting the data? In which context? Is it so you're talking about in general or available on HDInsight? On HDInsight, yeah. That's a great question. It's a little bit beyond the scope of this talk. Actually, let's talk about it in the context of the real-time pipelines, because we'll talk about a couple of the technologies for data ingestion, and then we'll talk about that. Okay, so data pipelining tools is a little bit more complicated chart than than we've seen before. So we have Azure Data Factory, we have Airflow, and as an example, stream sets. And we'll actually take a look at stream sets later. We'll have a demo of stream sets later after the real-time section. So just to highlight a couple of things on this large slide. So if you think about Azure Data Factory, so it's a great managed service, so you don't need to host anything. It provides you with SLA. So in that regard, it's very trustworthy, reliable service. But in terms of limitations, it doesn't have a UI to create your pipelines. And if you need something like that, then it's not available. So fortunately, in the next session, you'll have a glimpse of the UI that the team is building, so that problem will be resolved. One of the larger limitations that is now actually in the past was support for on-demand Spark clusters that wasn't present in ADF till today. But today, with the release of the Azure Data Factory v2, it is actually available now. For now, from the Python interface, and soon from the UI as well. So on the side of the Airflow, you would use it when the limitations of the Azure Data Factory are limiting, or when Azure Data Factory doesn't fulfill your needs due to its limitations. So then your choice could be an Airflow as a build-it-yourself toolkit, where you can extend it in any way you want, and it's fairly easy to do using Python. And finally, stream sets that we'll take a look later. You'll see in the demo that it's like 2 steps above in terms of capabilities of this other two tools. It supports not only batch pipelines, but also real-time pipelines. It has great UI with a rich set of components to build your pipelines from. And in that regard, that kind of provides superior experience, but it's a third-party kind of tool. Any specific questions on the data pipeline technology choices? Okay, let's move forward. So great, we get to real-time pipelines. So just connecting to our very typical use case of incremental data processing. So one of the primary limitations of this very nice way to process data in a small chunks in an incremental way is the fact that if your job needs to build some form of aggregation or insight that involves the full data set, then this incremental data processing pattern doesn't apply. Because like in the simplest case, if you just want to count all of the events that you have seen so far, you cannot do that if you process data incrementally, because the input for the job only has this latest snippet of data. It has no information whatsoever about all of the previous information that is available in your data set. So while it's very convenient in terms of resources, it's very limited in terms of its capabilities. So this is where this idea of streaming data processing comes in. It resolves this fundamental limitation. It says that, hey, why don't we put all of the states that we need for our job to complete in the compute engine itself. So we'll introduce a notion of the state of the streaming data processing engine. And then we would still be able to process data in an incremental way, even up to the granularity of processing a single event at a time. And the compute engine itself will actually maintain all of the state that it needs to maintain in order to produce any analytics that we want. So on the example of the simple count, we can see that every time we execute process some new event or new micro batch of the data, we would retain all of the relevant state information that is needed for us to compute this, for example, a running count of all of the events. So in that kind of scenario, we can use still Spark to process that. And one of the important kind of considerations here with real-time jobs is that now that they kind of run all the time, and you need to keep this state in your cluster around, your cluster now needs to operate 24/7, or it becomes a real-time system. And one of the requirements of real-time system is high availability. So one of the features of HDInsight that it provides you with ability to run your Spark streaming jobs in a highly available manner. That means that even in the case of node failures, the proper failover mechanism will be triggered, and your job will be able to continue execution and retain its real-time state that is important for real-time computations. So in the first in the first streaming pattern, what we see customers do is just processing the stream of events from a variety of sources, and this is where we talk about the way to ingest your events into the system. So one of the ways is Event Hub. It's basically a queue, a distributed queue, where you can land your real-time events and then consume on demand from your real-time system. And alternative coming from the open source is Kafka, which is available on HDInsight as well. So Kafka is another implementation of the kind of distributed queuing system that allows you to ingest real-time events. In addition to that, you can also just process files from the Azure Blob Storage or Data Lake and treat them as an incremental kind of, whenever new files appear, you trigger your streaming job to process these new files on demand. And in the first pattern, we are simply pushing data or new computations into real-time dashboards on the web application or mobile applications or in a Power BI. So what are the choices from the streaming technology point of view? So as we mentioned, Spark structured streaming is the latest kind of version of the streaming support from Spark. Then one of the older technologies is Storm, and it had a very great adoption. In the past, it was available as one of the first streaming technologies. And it still is widely used and fully supported by HDInsight. But in terms of adoption now, we see new projects are moving towards Spark structured streaming. And finally, one of the new contenders was Project Flink. And in the latest kind of years, we see it's been used in conjunction with another kind of library in the open source world called Beam. So that library provides you with kind of abstraction APIs that allow you to use and streaming technology of your choice. The Beam written program can function against Flink, or you can switch it at runtime to function against Spark. So from this table, you can see that basically from the adoption point of view, Spark is leading the choice here. And in terms of technology, one of the big points of Spark was latency that is being addressed with the latest version. And that kind of makes your choice more or less clear in terms of what would be the technology choice moving forward in terms of streaming technologies. Any questions here? So the question is, how do you compare these technologies with IoT Hub? Yeah. So IoT Hub is actually, so on this picture, that's a great question, thank you. So on that picture, we are comparing only streaming engine technologies. So the technologies to process the events. IoT Hub that connects to Event Hub is ingestion technology. So it's not part of that kind of technology landscape. You need streaming engine and ingestion engine at the same time. Yeah, absolutely. Thank you for bringing this up. So there are many other technologies on Azure available, like Stream Analytics, Azure Data Lake, and in the end of the session, I have references to kind of a broader scope architecture design kind of discussions where you can hear about them. For this session, we decided to go deeper into the Spark-related and open source-related architecture, so those technologies kind of out of scope, like just not possible to cover everything. Yeah, so Azure Data Factory, Azure Data Lake and Stream Analytics are the proprietary technologies available on Azure. Yeah, that's correct. Okay, yeah. Is Kafka integrated on HDInsight? Yes, that's correct. So we have Kafka cluster type available on HDInsight as a first class, fully managed offering. Thank you. What's the difference between Spark and other ETL tools? Yeah, so that's a great question. So you mentioned two technologies, SSIS and Informatica. So SSIS lands in the area of data orchestration tools. And as we speak, it is actually now part of the Azure Data Factory team. And they have some extended plans of how they integrate those two together. So again, I would refer you to this session later tomorrow, where you'll learn more about the future of SSIS and Azure Data Factory. Informatica is yet another third-party tool that is a big kind of offering in itself. So I would say it's one of the third-party tools that you can certainly consider, but it's out of scope for this session. Does HDInsight plans to integrate NiFi? That's a great question. We don't have plans like that at the moment. So HDInsight has application marketplace, and in the application marketplace, we offer multiple of the third-party offerings for real-time pipelining. And the one that we currently have is the StreamSets. We'll take a look at it closer. It is very similar in capabilities to NiFi. Yep. So the question is, when I tear down the cluster, how do I keep all of my metadata around, like code and metadata about tables? So that's two separate questions. The metadata about tables is preserved in the external metastore. So when you create a cluster, you can connect to the external metastore. That allows you to keep your metastore around outside of the cluster lifetime. And in terms of code, depending on your choice of the orchestration technology, your code would either live in the blob storage account, or it would live into some GitHub repository from which you would pull it into a cluster for the execution. Like with the Airflow, you would use the GitHub repository. With Azure Data Factory, as you've seen in the demo, you would keep your code in the blob storage account. Okay, so let's move forward. Yeah. That's a great question. So what is the cost model for these different options? So let's see. So Spark Structured Streaming and Storm are available as a cluster types on HDInsight. So the cost model for them would be the same. When you create a cluster, you pay for every hour that you use your cluster. The model for Flink, Flink is not supported as a first-class element or cluster type on HDInsight right now, but you can install it as a customization script. We call it script action. So if you install it on HDInsight cluster, then you would be having the same cost model as a HDInsight cluster. By itself, Flink is an open source technology, so it is provided for free. Okay, so we can move forward. So the next more advanced pattern on real-time processing just adds kind of a little bit of an important scale kind of element to the first pattern. So what if we need to serve millions of users, what if we need to serve results of our stream processing to millions of users? Imagine like one of the projects that we have is Xbox team is maintaining the leaderboards for all of the players on Xbox. So the computation of the leaderboards is performed in a streaming manner, but then millions of users from Xbox needs to retrieve these leaderboards. So how do you do this? You need to have this scalable serving layer, and one of the common choices for this is NoSQL, but you can use traditional SQL databases as well. So this outlines kind of your choices for the streaming layer, or for the serving layer. In terms of serving technology choices, that's another big topic in itself, but just to outline kind of at the high level, you have a choice of caching technology, NoSQL, and traditional SQL database. And in that regard, the primary factors here are scalability and management. So in terms of management, there are two different models. Like the Cosmos DB is a fully platform service, full platform service. That means that it isolates you from management of any type of hardware. On the other choice, on the other end, Redis Cache and HDInsight HBase are managed cluster form factor. That means that you still need to manage the lifetime of the cluster nodes. You still need to resolve issues if you have them on the node, unless they're automatically resolved by the system. But that adds additional management complexity. And on the scale side, all of these technologies like Cosmos DB and HBase have unlimited scale, and Redis have some limitations in that. So if your data size goes to some large sizes, then that makes your choice very clear. But if you exclude scale as a factor from the equation, and this is actually the case in many streaming scenarios, if results of your streaming processing are limited to, let's say, to just a set of your customers, and you have just millions of customers, and you just need to compute some statistics or some parameters for every of the customers. So how do you serve results of a table of millions of customers? Well, SQL Server here is a very solid choice, and we see many customers use SQL Server in the scenarios where the scale of the SQL Server is sufficient. Any particular aspect of that table that raises your interest? Yeah. There was graph in Azure SQL. Well, maybe there is some updates. Yeah, maybe I need to update my table. I don't know. Cosmos DB maintains its own data store. Yes, that's correct. Okay, so let's move forward. So now we are getting into the point where we starting combining the batch patterns with the real-time patterns. So how about interactive analytics on real-time data? So the common scenario that we see here is that there is all of these technologies that are optimized for kind of interactive data warehousing. And again, in the end of the slides, I'll have some references to other sessions with more details about that. And data warehousing is very heavy in terms of very heavy workload in terms of its demands to compute and overall configuration. One of the common limitations across data warehousing technologies, not all of them, but many of them, have a limitation that they need this data to be loaded in the data warehouse. So it's an inherently batch process. So how do you combine this data warehousing technology then with the demands of your business where you need to bring the latest real-time kind of data into the data warehouse? So in this scenario, and it's a very common scenario, the pattern to resolve that issue is to combine the streaming processing with batch processing. So the first, you process the kind of a bulk of the data from storage using batch technology and populate your data warehouse, represented here by Hive partitions, as a first kind of pass. And that kind of primes your data warehouse to be used by your data analysts. And in terms of data warehousing technologies, we are talking about a variety of technologies, like Spark can be used in such a way. There is a new entrant in the space, Presto. That's very popular among some of our customers. And on HDInsight, we have a new offering, kind of a next generation or new version of Hive called Hive Low Latency Processing. On HDInsight, it's available as Hive Interactive Query Technology that you can use also to run low latency data warehousing technologies. And on the third-party side, from ISVs, you also have a broad selection of choices. One of them available on HDInsight Marketplace is a company called AtScale, where it provides you a combination of data cubing technology or analytics service with the traditional data warehousing kind of capabilities. So once you populated these kind of high-performance data warehouses, then how do you incorporate the real-time data? Well, that you can do with a streaming technology, so you can process the real-time stream of events and generate these little increments of new data, and then append it to, potentially you can just directly append it to your data warehouse. Well, direct append here has a problem is that if you're processing these batches of data very frequently, then the files that you would be appending to the data warehouse would be very small as well. And one of the common limitations of these data warehouses is they stop working with an extremely large number of files. So the solution to that problem is to have the second phase of batch processing, where the small incremental files are aggregated further into larger partitions, and then you add these larger partitions to data warehouse. Just to summarize the data warehousing choices, so that table is actually one of the more challenging ones. There is no clear winner here, but they all kind of have their pros and cons. From the management side, it is important to kind of note that Azure SQL Data Warehouse provides one of the solid choices here, but it's not applicable in all of the scenarios because it has some limits right now in terms of maximum scale, and it does require ingestion into its own data store as part of this, as part of its technology. So it doesn't allow you to read data directly from the data lake or from Azure Blob Storage. On the other hand, other technologies like like Spark SQL and interactive query, they share most of the properties, and one of the highlights here is its ability to provide kind of security features on top of your data warehouse. So just a couple of years ago, the approach to data warehousing in open source space was fairly simple. You just give your kind of employees ability to run your queries. And from security point of view, nobody asks questions like who can read what data. If you give somebody access to the data, that implied that they can use this data warehouse and read all of the data. So technology didn't stop there. So now we are actually talking about very common requirement that comes from our customers and now supported by technologies where we say, hey, how about security? How could we forget about security? And now, fortunately, Spark and Hive, including interactive query, as well as SQL Data Warehouse, they provide very sophisticated techniques of how you can integrate your security policies and separate data sets between different groups of users and provide different levels of access to different groups of users. So here, Azure Data Warehouse provides kind of a standard SQL-based security where you can define your policies based on views and columns. And open source-based technologies make a little bit step ahead here, where they provide kind of provide you with the ability to define your security access policies directly on tables without introducing this notion of views, and as well as provide more advanced capability of data masking, where you can provide partial view of some of the columns to your employees. Any particular question on this table? It's big, so yeah. When you mention column view, is it? Yeah. That's a great question. Yeah, this description is a little confusing. Yes, you are right. Where we talk about column, this is well, in the SQL data warehousing column, you can define separately permissions on columns, and that would make the whole column kind of available or not available to your users. And separately, if you want to define which rows your users can see, you would need to define a view which kind of filters the data and then grant your users permissions to that view. So that's a kind of a two-step process. As opposed to Spark and interactive query, where you have ability to define your policies directly against the various conditions on the data. So you're basically defining directly which rows which users can see, which simplifies the whole process. You just maintain the policies, and you don't need to manage all of this views. In the SQL world, it results sometimes results in like in 1,000 views that you have to maintain with different levels of permissions for different users. So the point here is that Spark and Hive, at least at the moment, have more flexible ways to define your security policies. And actually, Azure SQL has this data masking and row level policies as well. It's just not available yet in the data warehouse. That's a great question. Thank you. So Presto, so in HDInsight, we have a set of cluster types where we support these technologies in a kind of in a supported manner. And Presto is not one of them. You can still install Presto as any other open source technology on HDInsight using script action as a custom component. But that means that you wouldn't get support from the product team for that technology. That's the meaning of this now. That's a great question. Yeah, I would love to incorporate everything, but I think we are already running a little bit out of time, even with the set of technologies that I have here. Again, in the end of the session, I have pointers to the sessions that cover data lake analytics. Okay. So, and final pattern in our real-time data systems. And that's a very big one. And again, there is a separate session dedicated exactly to this single pattern. And you'll get a pointer to that one. But you cannot talk about patterns of the data pipelines without mentioning the Lambda architecture. And that's a very flexible and powerful technique. And that's why it kind of gathers so much attention. And the idea behind Lambda architecture is kind of natural based on the patterns that we have covered so far. It just kind of makes a final logical conclusion. So the Lambda architecture kind of idea is combining the real-time data processing with batch data processing. And when we talk about Lambda architecture, this notion of real-time and batch is taken to a very generic level, where we say, hey, in batch, we can do either ETL or machine learning processing, and maybe some graph processing, and just process the bulk of the data kind of at once and generate some baseline knowledge or insight about our data. And then we augment that insight with the latest real-time data by using streaming technologies that we have discussed in what's called speed layer. And then the critical point here is merging of these two. And the merge place for these two streams of information is usually a NoSQL database, because this merging in general implies that you need not only to append data, but also update various properties or columns of your data. So that merging is kind of a transactional operation. And NoSQL databases are used frequently for that. So that's the idea behind Lambda architecture. And In terms of serving of this kind of merged information, there is, again, variety of technologies available, including data warehousing technologies and NoSQL databases. Okay, so any questions on Lambda architecture? It's a big topic, so please limit the questions. Yes? So you mean AWS Lambda service or Lambda architecture? Lambda architecture is fairly generic term. Yeah. So that service is separate. Yes. Yeah. AWS polluted all of the information space. Yeah. So Lambda is a term that was introduced quite some time ago that refers specifically to this very generic pattern, and it can be implemented by a variety of technologies. Originally, it was introduced around the notion of NoSQL databases, because NoSQL is the place where you merge these two insights. But after that, it's expanded towards a variety of technologies that can be used to implement Lambda architecture. So it has nothing to do with AWS Lambda. Okay, so let's do a little demo. So for the demo, we'll use stream sets. Because of this kind of integration of third-party applications in HDInsight, it is very easy to create one. We'll skip the creation step. When you create a cluster, you can just select from the list of applications. I don't know if no, I don't have. You can just select the stream sets in the list of applications and say, hey, just deploy this stream sets application on top of my HDInsight cluster. Once you have it provisioned, then you can access it from the Applications tab. So you just open the portal, and you arrive at the stream sets web application. And as you can see, this is some graph of steps represented visually. So that's the kind of visual design interface for your batch and real-time jobs. So you can define both of them using the same designer. So here you can see a very simple example where we read data from Twitter and do some real-time processing of the tweets. So on this box, you can see that, hey, we are just reading from some HTTP URI. Then we have a selector box where we define what should happen to these events when they flow through the system. And it's a simple condition that, hey, if delete verb exists in the event, just send it to pipe number 1. Otherwise, send it to pipe number 2. It's a simple filtering condition. Then we have an expression evaluator that simply maps values of the tweet into columns. Then removes some of the selects some of the columns that it wants to keep, and finally writes them in the form of the files. And the Hadoop file system element has a reference to a blob storage. So WASB is a designator of the Azure blob storage as a file system. So that means that these tweets will be saved into a blob storage account. So simply like that, just from the looking at this definition of the streaming job, we were able to understand what it's going to do. And it's easy to run it, so I just click run, and behind the scenes, stream sets would spin up either a local job that would execute this, process this event, or it can actually spin up the Spark application in the HDInsight cluster and run this job at scale in a distributed manner as a Spark application. Okay. Can you repeat that, please? Mm-hmm. Does stream set application run inside of the cluster, or can it run outside? So in the current model, the stream sets application runs inside of the HDInsight cluster. Yeah, and right now it's one of the limitations that it cannot run outside. Okay, and what is happening with our demo student? Okay, let's give it a try. Okay, 1 second. Okay, apparently something happened with Twitter, so it doesn't generate any data. What happens? So one last piece here of the demo is if you look at the data pipeline itself, then there is this parameter here that defines how it will run. So it can run in a standalone execution mode, or it can run as a cluster yarn streaming. That means that it will create Spark streaming application in Yarn cluster, in Yarn HDInsight cluster behind the scenes. Okay, so let's switch back. So we are just about the end of our session. So this is the references that I kept promising you about throughout the session. So the first one is architecting your big data solutions with SQL data warehouse and analysis services. So that one takes a high-level view and kind of discusses other services in Azure as it pertains to big data processing. So that would give you kind of a more broader perspective. Then the data factory session about the capabilities of the V2 version is called New Capabilities for Data Integration in the Cloud. So certainly recommend attending that one. You'll get a glimpse of the new UI-driven data pipeline creation tools offered by Azure Data Factory. Then there is a very interesting session about machine learning and Cosmos DB using Spark. So that's real-time data science with Azure Cosmos DB. That's a very good example of the Lambda architecture. It's a very concrete implementation using a technology stack available in Azure. And finally, another Lambda architecture related session is streaming big data on Azure with Kafka, Storm, and Spark. So that session is heavy on the ingestion side. So if you want to learn more about Kafka and Event Hub and pros and cons between those two, this is the session that covers that. And finally, I mentioned in the data warehousing space that security is becoming one of the kind of fundamental requirements in the big data space. So enterprise security and monitoring for big data is covering all of the details of security implementation on HDInsight. And finally, one more session on machine learning pipelines is Microsoft makes artificial intelligence real. And if you want to try new capabilities of Azure Data Factory in PowerShell, the demo that we tried, the first demo, so then it's already published. So here's a link to the documentation where you can go and repeat the demo yourself. Okay. And now I'm ready to take more questions if you have them. Thank you for attending the session.